In SPC8, we're going to spend another lesson on the photoelectric effect now. So we had our first lesson where we observed the phenomena on those gold leaf electroscopes and described what's going on and why it's happening. In the second lesson, we introduced this electron volt, which we're using to measure some of the energies that we're coming across while discussing the photoelectric effect. And what we're going to do today, we're still not actually going to introduce any more theory. Oh, that's not the one I wanted. There's not going to be any new theory. But we're going to have a look at what we can do with what we already know, and we're going to have ourselves an experiment and plot a lovely graph. So what we know from Einstein's equation is that HF equals a half mv squared plus phi. So what can we do with this? Because if we're going to plot a graph, we're going to want to have a y equals mx plus c again, aren't we? So y equals mx plus c. Oh god, where on earth do we even start? Well, the first bit's easy. These two are clearly a plussing of each other. Then we've got this mx and a y. Well, actually, these are going the wrong way, aren't they? So here we've got two things, here we've got something else. And so what we're going to have is a half mv squared is equal to hf, and it's going to be minus phi this time. So this is this equation rearranged. And so we can get a straight line equation if we can plot the kinetic energy, and remember this is the a half mv squared max, against the frequency of light. So remember, we're talking about a plate, a metal plate, and it's got these electrons in on it. Our photons are instant upon the plate, and whizzing off comes our negatively charged electrons. So our photons with energy hf, then coming off we have electrons with energy up to a half mv squared max. And then we lose some amount of energy, the work function in the metal. So if we can know what energy we're putting in and measure the energy of the photons coming off, we could plot a half mv squared max against frequency, and that would give us a y-intercept of the work function. So we could find out the work function of this metal. We could work out what that is through this experiment. But also, the gradient's going to be h, though this Planck's constant, this fundamental constant. So we'll be able to measure the gradient of this graph, and it will tell us one of the fundamental constants in nature. So one of the really profound fundamental constants, if we can do this. So how on earth do we measure the frequency of light? And how on earth do we know how much energy these electrons are coming off? Because we certainly can't measure their speed. We might be able to look up their mass, and in fact in A2 you'll work out how we can kind of measure the mass-ish. But we're certainly not going to be able to measure their speed. They're going to be flying all over the place, and anyway they're far too small for us to see. Well, let's start with the frequency. Well, that's quite straightforward. We can just put a filter in front of a light. So if we have some light bulb, then that's going to emit some light, and we can put a filter in front of it. So we can say have a red filter or a blue filter or so on and so forth, and we'll know which frequencies are getting through the red filter. Through the red filter is going to be the red frequencies, through the blue filter it's going to be the blue frequencies. So we can have our light shining through a filter onto our metal surface, and that way we'll know what our frequency is. So we can tick that off. So how do we find this kinetic energy? Well, let's flick over to the sides, and this is what we're actually going to use. So this is our light coming in, and we said this is going to be passed through an optical filter so that we've only got particular frequencies coming through. It's going to land on our metal plate. And what's the rest of all this about? Well, remember we said that the electron volt is the energy. Let's clear this off now. You can rewind the video if you need to have a look at it again. So we said the electron volt is the amount of energy which an electron gains or loses when it passes between some potential. So let's have a look. Let's zoom in on a bit of that diagram that we've got in the slides. And let's have a look at this. So we've got this is our metal plate. This is our light instant on it at some known frequency f. And the electrons are then going to come whizzing off with some energy, a half mv squared max, up to a half mv squared max. And so we're going to actually have electrons travelling from here to here. So you'll remember that in the diagram, this end was connected to an oscilloscope, this end went through the rest of some circuit, and then joined up at the other end of the oscilloscope. So actually we've pretty much got a circuit. And within that circuit, there was a cell. Now have I done that the right way around? Because that's going to be positive, that's negative. No, that cell's the wrong way around. We'll see why in a minute. So this electron's going to come off there, it's going to whiz over here, and if we stick an ammeter in here, then these electrons moving across here are going to cause some current. And so what we can do is if we can change this voltage, so if this is a variable voltage, then we can set some voltage across these two plates. So we're going to have a... Actually, it was right the first time round, wasn't it? Screw all that. Use this one here. I mean, it's not that important. But, so if we charge these plates such that this is positive and this is negative, then while the electron moves from this side over to this side, it's going to lose some energy. So if the voltage is V, then it's going to lose V electron volts. So if it was 5 volts across here, then the electron's going to lose 5 electron volts as it passes across. And so what we can do is we can change the voltage across it. Let's screw this in. This is a bit messy down there, isn't it? Let's polish it up a bit. So there's our positive, there's our negative. So positive on the positive plate, the negative is on the negative plate. Where was I? Yes, electron coming from this side, moving over to this side, is therefore passing through a potential. It's going to get sucked back towards the positive and repelled away from the negative. So moving from this plate towards this plate is going to lose energy. And what we can do is we can change this voltage until this current reaches 0. Because without a voltage, the electron passes across and we get some current. Once we apply enough voltage, as we increase the voltage, the electrons with the lower amount of kinetic energy aren't going to be able to reach the other side, and so the current's going to go down. As we increase this voltage, we're eventually going to get to a point where even the ones with a half mv squared max have lost all of their energy going across this potential, and so they're not going to have any energy left when they get to the other side, or they're not even going to reach the other side, and so there's not going to be a current passing along. And so what we can do is we can vary this voltage until we just about reach 0 current on our ammeter, and we then know that this voltage is what's required to make the electrons lose a half mv squared max. And so if we have, for example, if at green light we require 5 volts to stop this, then that's one data point. We know that green, whatever that frequency is, requires 5 electron volts worth of energy to stop this. So on our graph F against half mv squared, we've got green against 5 electron volts. And then we might change up to blue. And remember Einstein's equation, that's HF equals a half mv squared max plus phi. Phi is the same, so if we increase the frequency, we're going to have more kinetic energy left over. So with the blue, it might now be 7 volts is required to stop this. And so our next data point is going to be blue requires 7 electron volts. And so that's what we're going to get. We can change this in incident frequency of the light. We can change the voltage across here, and that corresponds to the half mv squared max when we reach zero current. So that's what we're seeing here. We've got voltage, so we can measure what this voltage is. We can also measure it in the oscilloscope if you really want. Oh, I guess we're using the oscilloscope as the ammeter, aren't we? We've got the cell. This little contraption here, you'll be introduced to that later into the course, but that's used to change what the voltage is that comes across here based on a fixed bit over there. Anyway, light instant comes across here, but in doing so, it's got to work against this potential, and so eventually we reach zero voltage. And we can plot a nice graph from this. So let's clear this all out and have a look at what sort of graph we expect. So we said we were going to have a half mv squared max equals hf minus phi. And so our y-intercept is going to be negative, and our gradient is going to be h. So what we're going to have is our ke up here, and our frequency along here. Now our y-intercept is negative, so what we're going to get is a line like this. And if we could measure negative kinetic energies, which we can't, whoops, what have I done? There we go. If we could measure negative kinetic energies here, then this here would be our threshold, our work function. So although we can't measure this bit, we know it's a straight line, so we can extrapolate it. And this is going to be minus phi. So the value down here, if it's say minus 2 electron volts of kinetic energy, then our work function is going to be is going to be 2 electron volts. And we can also measure here, so this x-intercept is going to be the minimum frequency required for something to come off. So we can see at these lower frequencies nothing's coming off at all, no matter what we do with the potential, but above here we get something coming off. Above this frequency we get electrons coming off. So this is our threshold frequency that we discussed earlier. And then our gradient, so if we do our delta y by delta x, delta y over delta x, then our h is going to be delta y over delta x. So we can measure the gradient to get Planck's constant, our fundamental constant. We'd expect that to be the same for anything. So if we were to do this with something else, we'd expect the gradient to be exactly the same. The work function might be different. So the y-intercept would be different and the threshold frequency would be different, but this fundamental constant, this unchanging constant, the constant is going to be constant, and so the gradient's going to be the same between different materials. So that's the sort of graph we'd expect to plot when we do this. Slightly tricky to get your head around what we're doing to reach this graph, but hopefully you've been able to follow along.